At the edge of the solar system, far beyond Pluto and the icy worlds of the Kuiper Belt, there may be something vast and invisible. A frozen sphere of ancient objects spread out like a halo around our sun. We've never photographed it. And yet, for decades, scientists have been almost certain it's there. They call it the Oort cloud. The Oort cloud sits at the boundary of what we know and what we think we know. Could something out there be disturbing it? An unseen star, a passing rogue planet, or something stranger? Is it possible the Oort cloud marks the physical edge of our universe? Or even the edge of our simulation? In 1950, a Dutch astronomer named Jan Oort proposed something that would change how we think about the outer limits of our solar system. He suggested that far beyond the planets, including Pluto, there might be a vast cloud of icy objects. The clues, he believed, were already in front of us, hidden in the strange orbits of comets. For centuries, comets had puzzled astronomers. They would appear in the sky suddenly, often trailing long, glowing tails, and then vanish just as quickly. Some returned again after many years, while others never came back. Astronomers had been tracking these objects for a long time, carefully noting their paths across the sky, and by the mid-20th century, enough data had been collected to see patterns emerge. The key clue was the shape and speed of the orbits of long-period comets. These are comets that take hundreds of thousands, sometimes even millions of years, to circle the sun. When astronomers looked closely at these comets, they found that many had extremely distant aphelion or farthest points from the sun. The starting points of their journeys seemed to lie far beyond the known solar system. More curious still, the directions they came from appeared random. If the icy bodies beyond Neptune were arranged in a flat disk, we would expect to see comets entering from roughly the same plane. But that's not what we observe. Instead, long-period comets appear from all directions in the sky. Some come from above the solar system's plane, others from below, and some arrive almost sideways. That kind of pattern only makes sense if they are coming from a large three-dimensional structure, something like a sphere. Oort began analyzing the mathematics behind these cometary orbits. If the comets had been orbiting the sun for billions of years, making passes close to it and then swinging far away again, their orbit should have been more tightly wound. Gravity, collisions, and other forces over time would have reshaped their paths. But these comets didn't show signs of long-term wear. Their orbits looked fresh, almost like they had just begun their journey into the inner solar system. This was a big clue. Oort realized that many long-period comets had probably only made one trip into the solar system. That meant they were coming in from the outside for the very first time. So where were they coming from? Oort theorized that these comets must be stored in a kind of reservoir far away from the sun, a place where they could remain frozen and untouched for billions of years. Occasionally one of these icy bodies might get disturbed and be nudged into a new path. Once disturbed, it would fall toward the sun, becoming a comet with a long, arcing orbit. He estimated that this cloud must begin tens of thousands of times farther from the sun than Earth is. In fact, he proposed that it could stretch out nearly a quarter of the way to the nearest star. This was an enormous distance, far beyond where any planet or asteroid had been seen. Oort wasn't suggesting a neat organized ring like Saturn's or the asteroid belt. He pictured something much vaster and more diffuse, a giant sphere of icy fragments all slowly orbiting the sun from afar. Each object in the cloud may be separated from its neighbors by millions of kilometers. This idea helped answer a number of long-standing questions. For one, it explained why comets could still be so bright and full of ice even after billions of years. If they had spent their lives in the inner solar system, they would have long since melted and faded. But if they spent most of their time in a dark frozen region on the solar system's edge, their icy cores could remain preserved. Oort wasn't the first to wonder about the origin of comets. Earlier in the 1930s, an Estonian astronomer named Ernst Öpik had also suggested that comets might come from a distant unseen cloud. But it was Oort who took that early idea and expanded it, putting numbers to the distances and studying the actual orbital data to support the theory. Because of this, the concept became closely tied to his name. Today it's known as the Oort cloud, though some also call it the Öpik-Oort cloud. Over the years, scientists have come to believe that the Oort cloud has two main parts, an outer region and an inner one. Most people only hear about the outer part, the one that sends long-period comets flying in from deep space. But hidden closer in, there may be another layer, a dense and quieter region called the Hills cloud. This part is sometimes called the Hills cloud, named after astronomer Jack G. Hills, who proposed its existence in the 1980s. The outer part of the Oort cloud is believed to begin at around 20,000 to 50,000 astronomical units from the Sun, and may extend out to 100,000 or even 200,000 astronomical units. At this distance, the Sun's pull is incredibly weak. Objects out there are barely bound by its gravity. The tiniest push from a passing star, a molecular cloud, or the gravitational tides of the Milky Way can knock these bodies off course. The Hills cloud is believed to start somewhere around 2,000 or 3,000 astronomical units from the Sun and stretch out to 20,000 or 30,000 units. It's much closer in than the outer cloud, but still far beyond the orbit of Neptune. Objects in the Hills cloud are held more tightly by the Sun's gravity. Because of that, they are not as easily disturbed. They stay put, waiting in silence for some rare event. If the outer Oort cloud were the only source of these icy visitors, we would expect it to run out more quickly. The outer cloud gets drained by gravitational nudges that fling comets away forever. Some researchers believe that as much as 90% of all the mass in the entire Oort cloud is stored in the Hills cloud. That means most of the icy bodies orbiting beyond Neptune are not sitting at the extreme edge, but are gathered in this inner zone, hidden and untouched. The early solar system was not a calm place. It was wild and violent. The Sun had just formed from a swirling cloud of gas and dust, and all around it clumps of matter were sticking together, colliding and growing. Some of these clumps grew large enough to become planets, others were swept up by those planets or thrown into the Sun, but not everything found a home. Some objects were pushed away. These misfits, too small to grow into worlds, too far to be pulled back, ended up in the outer reaches. The idea that the Oort cloud is a leftover region goes back to the way comets behave. When astronomers study the ingredients in comet tails, water ice, carbon compounds, frozen gases like methane and ammonia, they see a kind of time capsule. But it also means that the Oort cloud isn't some smooth or elegant structure. It's more like a vast junkyard, a place filled with objects that never found a purpose. Some may be oddly shaped, cracked, or partly broken. Others might be combinations of rock and ice frozen together by chance. No two objects are expected to be exactly alike. Some scientists think that the story of how these objects got there is tied to the movements of the giant planets, especially Jupiter and Saturn. As these massive worlds grew, their gravity began to influence nearby material. But it wasn't just the planets that shaped this icy shell. The galaxy itself played a role. The Sun, as it orbits through the Milky Way, passes near other stars and moves through giant clouds of gas. Some researchers have wondered if the Sun in its early days may have stolen material from other stars. If the Sun formed in a dense cluster, a nursery filled with other young stars, then their gravity fields would have been overlapping and chaotic. For a long time, people thought the solar system ended where the last planet orbited. Once you got past Neptune, that was it. But as our knowledge grew, we realized that gravity stretches much farther. So where then does the solar system really end? That depends on how you define it. One way to think about it is by gravity. As long as the Sun's gravity can still hold on to something like a comet in the Oort cloud, it's part of the solar system. And by that rule, the solar system could be up to 2 light-years across. But gravity isn't the only way to define a boundary. There's also something called the heliosphere. This is the bubble of space created by the solar wind. The constant stream of charged particles the Sun sends out in all directions. The solar wind pushes against the gas and dust floating between the stars. At some point, the pressure from the rest of the galaxy pushes back hard enough to stop the solar wind. That place is called the heliopause. In 2012, something important happened. Voyager 1, a spacecraft launched in 1977, crossed the heliopause. For the first time, a human-made object had left the bubble of the solar wind and entered interstellar space. This shows just how fuzzy the boundary really is. You can define the edge of the solar system in several ways. If you go by planetary orbits, it ends with Neptune or Pluto. If you go by the solar wind, it ends at the heliopause. Scientists often use the word interstellar to mean space between stars, not just outside a planet's orbit. But even then, the idea of a boundary becomes tricky. The space between stars isn't empty. For now, the Oort cloud marks a kind of soft edge. It's where our solar system starts to blend into the wider universe. Beyond it, the stars take over. Their gravity becomes more important. Our solar system moves around the center of the Milky Way, completing a wide orbit that takes hundreds of millions of years. Along the way, it passes through different regions of space. Sometimes those regions are more crowded, and sometimes another star wanders close enough to make a difference. To be clear, close in space doesn't mean what it means on Earth. One of the most talked about is a small faint star named Schultz's star about 70,000 years ago. It's believed to have passed within less than a light-year of the Sun, possibly right through the outer edge of the Oort cloud. There's also another force at work, the tide of the galaxy itself. Just as the Moon causes tides on Earth, the Milky Way has its own kind of pull. This combination of passing stars and the galactic tide helps explain why the Oort cloud is spherical. That makes sense if it's constantly being pulled at from all sides over billions of years. Some scientists think that these constant nudges may also be one reason we still have an Oort cloud at all. In this way, the galaxy helps deliver these ancient visitors. The idea of Nemesis came from a pattern, one that seemed to show up in Earth's history buried in stone. Around the early 1980s, a pair of physicists, Richard Mueller and his colleagues, noticed something strange while looking at extinction events in the fossil record. Mass extinctions, those sudden disappearances of life, seem to happen not randomly but in regular intervals. Roughly every 26 million years, something catastrophic seemed to strike Earth. The theory that followed was bold. What if the Sun had a partner, a companion star, orbiting far beyond the planets? Every 26 million years it might swing in close enough to disturb the Oort cloud. They imagined this companion star as small, dark, and hard to find. It wouldn't shine like our Sun. It might be a red dwarf or even a brown dwarf, a failed star that never truly ignited. The name Nemesis came naturally. In Greek mythology, Nemesis was the goddess of vengeance, an unseen force that arrived to punish and restore balance. A companion star like that, they believed, would act like a galactic troublemaker, stirring up the outer cloud every time it passed near. And for years astronomers searched for this invisible twin, but Nemesis remained elusive. No telescope could find it. Infrared sky surveys, which could spot cold stars and brown dwarfs, turned up nothing in the right range. Still, the concept of a solar companion fits into a broader picture of how star systems work. Many stars in the galaxy are not alone. In fact, more than half of all Sun-like stars are part of binary or multiple star systems. A companion star on a long looping orbit would move slowly through the darkness, taking tens of millions of years to complete a single circuit. The Shiva hypothesis, named after the Hindu god of destruction and renewal, suggests that every so often something disturbs the Oort cloud and sends a wave of comets crashing into the inner solar system. With enough speed and size, a single impact could set off a chain reaction. Dust blocking the sun, temperatures dropping, food chains collapsing, life on Earth would change overnight. Supporters of the Shiva hypothesis began pointing to one extinction event in particular, the one that ended the age of the dinosaurs. About 66 million years ago, something massive hit the Earth near what is now the Yucatan Peninsula in Mexico. The crater it left behind, called Chicxulub, is more than 100 miles wide. All around the world, a thin layer of rock marks the moment it happened. The Oort cloud remains one of astronomy's greatest mysteries, a vast, invisible frontier that may hold the keys to understanding our solar system's past and future. At the edge of everything we know, in the cold darkness between worlds, ancient sentinels wait in silence.